Now we need to study AC voltage controller for highly inductive load. In this case we are considering bidirectional AC voltage controller for highly inductive load. So it is angle control methods we are studying for highly inductive loads. Here I have shown this is our power supply, AC power supply. So Vm sin omega t is an inputs. In positive half cycle, thyristor T1 conducts after we apply the gate pulses to thyristor gate of this thyristor T1, and in the negative half cycle, thyristor T2 conducts here also after we apply the gate pulses to the gate of this thyristor T2. The firing angle of the thyristor T1 and firing angle of the thyristor T2 we can change by changing the delay angle of the pulses. Based on the firing angles of the gate pulses whatever we are applying to T1 and T2, the load voltage RMS value will change. So here we are considering the inductive loads, heavily inductive loads or highly inductive loads. So motor coil is one example for highly inductive loads. So next, here I can show you the load voltage. The load voltage starts at alpha and it goes on this way, it goes on this way, goes till beta. This waveform is a current waveform. Current also starts from alpha and it goes till beta. One important thing here we need to hear, at pi the load current is not zero. So means what is the meaning? Now thyristor T1, this if you call thyristor T1 is conducting, means even at pi the thyristor T1 is conducting, means at the end of the half cycle thyristor T1 is conducting. So the input voltage is delivered to load even after pi until the current which is passing through thyristor T1 reaches to 0. Somewhere here the current through T1 reaches to 0, that angle I will here onwards I will call as beta. Okay, so my thyristor T1 passes my input voltage to load from alpha to beta. That's the reason I can say that my load voltage begins at alpha, it ends at beta. The load current also begins at alpha, it ends at beta. This is because my load is inductive load. In the similar way, in the second half cycle, so at this angle is somewhere here, this angle is beta, this angle is beta, sorry, what I am saying, this angle is pi plus alpha, this angle is pi plus alpha. At pi plus alpha we fire thyristor T2, so thyristor T2 transfers the input voltage to load. So the entire negative half cycle after pi plus alpha is delivered to load. This is the angle at 2 pi. You can see here at 2, see this is my current, negative current is flowing during negative half cycle. But one important thing is at pi you can see here the current not reached 0 because it is an inductive load. That's the reason current continues to conduct even after 2 pi, meaning thyristor T2 is in on state. So in negative half cycle also even after 2 pi current continues, so that whatever input is delivered to load even after 2 pi. So this again, once the current reaches to 0, thyristor T2 stops. Till there the load is receiving my input voltage. That's the reason load is voltage is reaching 0 somewhere here. Okay. So this is what we have seen, and we are familiar with the nature of an inductive load. So it is possible. Okay, next we need to calculate the RMS values for this voltage waveform. For this waveforms, we need to calculate RMS value for this waveforms. So you can see here, this is my waveforms. For this we need to calculate RMS value till here, till here. You can consider beginning of this waveform is this part, this timings I am considering period of this waveforms. I will take from here to, sorry, here. I will take from here to here. I will take this as my period. Sorry, not from here, till here. Till here. Okay, from here. I will take period of my waveforms. So it starts at alpha, it continues till beta. If you call this as a beta, then how do you call this angle? 2 pi. So where to, okay, sorry, we should take a periodicity till here, no, sorry, we should take periodicity till here. Now this means I can redraw it. This I will start periodic waveform like this. This is a period. This is one continuous waveform cell. This starts at 0, alpha, this is pi, this is beta, this is pi plus alpha, this is 2 pi. How can I call this? That's the questions. So if this is my beta, this is my beta, here to here it is pi, here to here it is what? You can see here, from this is to this beta, means again from here to here, if for an example beta is 110 degree, here to here is also angle is 110, correct, no? To duration means this width is 110 degree, 110 degree. 110 degree. Here to here it is 110 degree. So sorry, if you call you can say approximate values. This is 180, this is 180. So this is from 60, 120, 120, 130. If you call this as 130 degree, this is also 130 degree. So then if you call this as a beta, beta means starting from 0 till here, I will say it is beta. Then from here till this it becomes beta, this duration becomes beta, and this is what? Pi. So this becomes pi plus beta. I can call this as pi plus beta. What I am saying, this duration is alpha, this is beta, this is pi plus beta. Okay, we need to integrate the waveforms from here to here. So we need to take root mean square values of the output. So output, load RMS value. We are taking the RMS values of the load voltage. Load voltage we have seen already. It starts from 0, but 0 to alpha 0. So no need to take. So integration we can start from root mean is there. So what is the mean? So mean is there. So 2 pi, mean is 2 pi. So is it 2 pi or not? Check. We are taking this as a pattern from where to where we are taking, from here to so we should take from here one pattern. I said this is my period. But again next onwards there is a problem here. If you take this as a period, you take this as a period, no problem. From here to here, again this is how much, from here to here, it is 2 pi. So this is alpha, this is beta. In the next cycle onwards we should take from here. Or else you can take from here till here also, no problem. Anyhow this value is 0, anyhow this value is 0. But non-zero values remains from alpha to pi plus beta, so in the denominator we can keep 2 pi. So alpha, it starts from alpha, goes till beta, right here it's root mean 2 pi square Vm squared sin squared omega t d omega t alpha to beta plus Vm squared sin squared omega t d omega t root mean square. So you can see here this is pi plus alpha, so I should say pi plus alpha, this is pi plus alpha, this is pi plus beta, pi plus beta. So then this is equal to one by 2 pi Vm squared you can keep outside, so 1 minus cos 2 omega t divided by 2 I will keep outside, d omega t integration from alpha to beta plus again this is 1 minus cos 2 omega t divided by 2 I have already kept outside here. Integration alpha pi plus alpha to pi plus beta. This is d omega t. This part and this part is same. That's the reason I can say 2 into this, or you can do it twice. So Vm squared 4 pi this is 1 omega t beta minus alpha, I will rewrite. So Vm squared by 4 pi beta minus alpha, then this integration is minus sin 2 omega t divided by 2 limit alpha to beta. Same thing here, plus this is beta minus alpha, because here it is 1 omega t alpha pi plus beta minus pi minus alpha, beta minus alpha, in minus cos 2 omega t integration sin 2 omega t divided by 2. So this limit pi plus alpha pi plus beta, so this is Vm squared by 4 pi, so this is beta minus so this is 2 beta minus alpha minus sin 2 beta minus and minus plus sin 2 alpha, this is 2 by 2, this is 2 by 2, in here minus sin 2 pi plus 2 beta, this is 2 beta, minus sin 2 beta by 2 plus sin 2 alpha by 2, sin 2 beta by 2, sin 2 beta by 2, sin 2 alpha by 2, sin 2 alpha by 2. So Vm I will keep outside, 2 I will keep outside, root of 1 by pi, so 2, or else Vm by root 2 I will keep outside, this 2 we'll see here once. Vm by 2 I have kept outside, 1 by pi sin 2 beta minus 2 alpha, 2 into beta minus alpha, minus sin 2 beta plus sin 2 alpha. This is the RMS values of the load voltage, RMS values of the load voltage. RMS values of the load voltage is by beta minus alpha, correct. Some people will write Vm by root 2 outside, this is nothing but V source, then that's 2 if you keep outside 2 pi, or else if you take it this beta minus alpha, okay. So So V RMS of the load I can write here. So in this Vm by 2 I can write as Vm by root 2, Vm by root 2, that 1 root 2 is taken inside, so that is 1 by 2 pi inside a root, inside a root, inside a root. Then this is my 2 beta minus alpha, 2 beta minus alpha sine sine 2 alpha by 2 minus sine, sorry, okay, you can see here also, right. See, this you can rewrite like this also. This is alright, here. So VRMS of the inch. Some people will take this 2 inside. So here root 2 begins, root 2 remains. So V RMS of the load. So can I write Vm2 into 2? Correct, no? Root 2 into root 2 I can write. This is 2. But once I will write as it is, how it is there in the last one. So 1 by pi, 1 by pi. Two beta minus 2 beta minus alpha minus sine 2 beta plus sine 2 alpha root. Okay, so you keep Vm by root 2 outside, and this if you take inside, 1 by 2 pi 2 beta minus alpha minus sine 2 beta plus sine 2 alpha Vm by root 2 is V source, then 1 by pi, this is beta minus alpha, this is minus sine 2 beta by 2 plus sine 2 beta by 2. You can keep in both manner, either like this or like this. Both are correct, you can stop. Otherwise somewhere here itself you this 2 you cancel with this 2, and you can write final answer in this way, or you can write final answer in any way. Anyway. Thank you. We will talk more about bidirectional AC voltage controller for highly inductive loads. So this is our power supply, this is our ACR with this conducts in positive half cycle, this conducts in negative half cycle, this is load. So we have already observed this is my load voltage and this is my load current. Okay, so we'll go to simulation and I will show you the same. This is my bidirectional AC voltage controller. This I will consider as a power source. This is a thyristor T1, it conducts in positive half cycle. This is a thyristor T2, it conducts in negative half cycle. So 3 millisecond is the delay time I have used. Here it is 13 milliseconds. Okay, this is my load. If I show the waveforms, see thyristor T1, to that T1 we are applying positive pulse somewhere here. Okay, that's the reason this is my input voltage. Whatever I'm showing here is my input voltage. This is my input voltage. This is my input voltage, and we are firing thyristor T1 somewhere here. That's the reason my load voltage begins somewhere here. Whatever this red color I am showing here is a load voltage, and this is my load current. The load current shows like this. It continues after pi and it conducts till beta. This angle we called as beta. At pi plus alpha we fire thyristor T2 using this gate pulses. That's the reason load voltage begins at pi plus alpha, it ends and again it goes till pi plus beta. The load current is also going till pi plus beta. So till now we have seen all those things, and we need to talk more about what is the voltage across this thyristor and what is the voltage across this thyristor during all these times. See here, this thyristor is conducting during from alpha to beta, correct? In the first half cycle from alpha till beta, means there is no low voltage across this, means it is conducting, means it is acting like a conductor. The voltage across this thyristor T1 is 0. The voltage across this thyristor T2 is 0 when it is conducting. When it is conducting from pi plus alpha to pi plus beta, it conducts. In the second half cycle it conducts. Whenever it is conducting, the voltage across this is 0, and whenever it is not conducting, voltage across this we need to identify. So if both are not conducting, when they both are not conducting, at the time voltage across this is 0, because if this is conducting, anyhow the voltage across this is 0. But when this is not conducting, if this is conducting, again the voltage across this is become 0, because when this is conducting, it is acting like a metal wire. There is no potential difference between this terminal and this terminal ideally. That's the reason there is no potential in between this terminal and this terminal, even though it is not conducting. So one simple thing is, when this is conducting, the voltage across this is 0. If this is conducting, the voltage across this is 0. If this is not conducting and if this is also not conducting, voltage across these two SCR will be the same as my input voltage. So that we can see here. See here onwards, so we are applying a thyristor gate pulses to thyristor T1. So this is an voltage across this thyristor T1. This is say 0 till beta. When beta onwards, thyristor T1 is turned off, and thyristor T2 is also in turned off state, because we have not applied gate pulses to thyristor T2 summary during these intervals. So from here to here, the voltage across thyristor is same as my input. Okay, so same as my input. So this is voltage across thyristor T1. So see thyristor T1. So what I am saying here, what is this part? This part is coming from this end, this part is coming from this end, this end. So whenever both SCR is in not conduction state, this is my voltage across SCR. So this is what I was shown here across my thyristor this. Okay, I can show you the thyristor voltage across this also, voltage across this. So this is thyristor T1. See, voltage across thyristor T1, from alpha to beta it is 0. From beta onwards, same as my input. From beta to this is pi plus alpha to this pi plus beta, it is 0. Again, same as my input, because during this interval and during this interval, both SCR is in off state. Okay, so better you write this. Okay, so I will remove this and I will add this part here. So this is my voltage across thyristor T1. Okay, so if for I think time being, you know, onwards you can understand now, this is where our thyristor T1 begins. From there until you fire from till beta, the voltage across thyristor T1 is 0, and from beta to again you fire the thyristor T2, the voltage across T1 is same as my input, because this is my input. I can show you. I will remove this part also for our okay, I'll remove this part. You can see here. So I will remove these parts. So you can see here. So this is coming from these points, and this is coming from this side. Okay, this side. So I will remove these parts. So see, if I show this is an input waveforms and this is a voltage stress across thyristor, voltage stress across thyristor is 0 from alpha till beta. From again this is from beta to pi plus alpha, same as my input. Again from pi plus alpha to pi plus beta, voltage stress is 0. So this is my voltage across my thyristor. Okay, so we have seen all these things right now. One more thing I will tell you here.